First, let me tell you what is this subject solid mechanics is. In third semester, you have gone through solid strength of material or SOM and its laboratories. And here, since sixth semester, we will go for the solid mechanics and its laboratories. In strength of material, when we have taught you, I have told you against your question is there is so many assumptions or so many empirical formula that takes place that is kept when to solve different problems. Against your queries, I have told you that this formula was derived on the basis of certain assumptions, and it found these assumptions on the basis of which these theories, these formulas, these empirical formulas are made is okay, is permissible. You can make this assumption over it and over which the formulas which you have derived is usable. This comes closest to the actual values. May not be exactly accurate, but actual values. So we have devised so many equations, so many formulas, and in so many different type of application of strength of materials like this, say beam, say stress, strain, what is the function of a beam, what is the function of a torsional bar, what is principal stress, etc. But actual case is not that simple. So based on further studies by eminent research fellows like Kochis, etc., and so many people, we have noticed that if we make that amount of simplification, it will not give you a very correct result. Or this correct result may be usable for the time being, but in actual practice, it may not be that feasible, may not be that usable. So we have to go to the scholars decided to go to the more details to get the more accurate results. Now question is, from where we have to start? In strength of material, we start in from stress and from strain and from Hooke's law. You can say that these three phenomena are the basis of strength of materials. And over this, especially, and yes, that is the fourth phenomenon, that is elastic limit. Based on this four particular notation, particular assumption, I mean certain items and certain theories, based on these certain theories of these four items, we have reduced so many things in strength of material. So if you have to do certain matter in details, we have to go through this stress, strain, Young's modulus, etc., or as well as your Young's Hooke's law, etc. So we have started like this. In your syllabus, it is shown that it is started with strain, not with stress. But here I will start with stress, because in my opinion, unless you know the derivation of stresses properly, you should not go for strains. And strain will be comparatively easier if you know the application of different equations of stresses. So I have started like this. But one of the most
Excuse me, sir. Sir, your voice is very low.
Very low.
I have, yes, sir.
Problem is I cannot shout out much. Possibly I'm in my highest volume. Try to do that because I'm showing you the way.
This time, sir.
Or distance.
Okay,
Your
sir.
voice is
Okay,
little
sir,
bit
we will
louder.
manage, we will manage, sir.
I am more distant now. Can you listen? Hello?
Okay, sir.
Is
Yes,
it louder?
sir. You are audible, sir. We will manage.
Hello?
Bye.
Is it louder?
Okay, sir. Okay, sir.
It is comparatively better.
Yes, sir. Is it good?
Yes, sir. Yes,
Then
sir.
I am just
Yes, sir.
only
Health first, sir.
almost at the I've placed my face on the monitor of my laptop. Okay, I have no objection.
Okay, sir.
Uh, whatever may be the problem, you must tell me.
Okay, sir. Continue. Continue.
হ্যাঁ কি বল হ্যাঁ কি বলছিস আচ্ছা আমি শুরু করছি now let us go to the problem itself no just 1 second. Before I do tell you something about this, my present classes, let me share you about certain points of vectors and scalars. I hope, I am not very sure, but I hope that you have gone through this vector algebra in your first or second semester mathematics classes. I will here this subject, solid mechanics, totally depends on vectors, scalars, and tensors. And time to time, which is relevant for you, I will explain. I will give you the notes. I have prepared all the notes. I will send you to you through LMS when it will be ready for you. Let us tell you few points about the scalars. I hope you all know, but I am recapitulating the matter a bit quickly. What is the conditions? What is called scalars? What is called vectors? There are quantities in physics and science, latter in not initially but latter characterized by both magnitude as well as direction. Means we have the quantities, not only the value, but from where to where it is acting. We should be clear. And what are those quantities which have both this direction as well as value is defined as scalars. And there are only limited number of such values, say displacements from one point to another, not the value of the amount of displacement, but value of displacement. Not only that, but also from where to where it is displaced. Velocity, not only the value of the velocity in meter per second or centimeter per second, but from where to where you are moving. Force, the amount of force you are applying, okay, it is always required, but in which direction you are applying this force? In which direction you are applying the force? Acceleration, your rate of change of velocity is there, yet it's increasing. From one position to another, you are going with a continuously increased velocity, faster and faster. But from where to where you are going, you are supposed to know. This is important. So these items, when used in the, you see, in this our solid mechanics subject, we use vector is used as vectors because we soon find it has certain specific applications. Generally, you don't have much work to do with displacement, velocity, etc., but force and as well as stress. But force is always important. From where to where and in which direction this force is applicable, which is important. But you will soon find there are certain items like stresses, shear or tensile. We are not using vectors, but we are using scalars because scalars is only a quantity. Only a quantity, and there is no question of its direction from where to where this is applicable or so. There's so many things which are all scalars, except only few which we are using as vectors. Just I'm telling you quickly. There is a directed line segment, say PQ. You see there is an arrow, but there are different type of denoting it. You may have a suffix over it, like say A, B, or N. At this fins PQ, a line from one point to P to Q to the point Q means a force is applied from the point P and its value is terminated at the point Q and it is applied from P to Q. It can be applied from Q to P. They are numerically same, but as a vector they are not same because their line of action is exactly the opposite. Here P is defined as initial point, and or you can say even that is the origin, and Q is defined as the terminal point or end point or terminus of the vectors. There are so many method of denotation of the vectors. Just one second. There is so many method of denotation. It will vary from book to book, from the application to application, but these are more or less common. A arrow over the A, where A stands for scalar, and A to the suffix arrows comes for vector. A to the power 1, A to the power n. This is the magnitude or length. It can give you again like this within two vertical lines PQ with a arrow over it. A, no arrow over it, but within two lines. A with an arrow, but within two lines, etc. Then that is scalar. Other quantities characterized by only magnitude, such as mass, length. Just one second. Say mass, weight, temperature. These quantities are only scalars. Mass don't have any direction. Weight don't have any direction, and temperature don't have any direction. They are called scalars. To distinguish it, how then that apart from the unit, such as feet, degrees,
Sir,
etc., scalars are nothing.
sir, I think weight has a direction.
কি বলো?
I think weight has a direction.
Direction?
Yes, sir. A weight.
No.
A mass doesn't have, but the weight does have a direction.
I'm afraid no.
Sir, because weight equals mass into acceleration. And mass is vectorless, but the acceleration is a vector, so that's why.
Shono. What is temperature? It is a measurement
temperature is scalar quantity.
No, I'm not talking about scalar or vector. What is your mass? Amount of matter which you have. Okay?
Yeah.
What is your weight? Bolo.
The amount of mass into acceleration.
Nothing more than. What is the temperature? It is a method of measuring the difference in heat of a particular quantity. Question is one thing. Do you have any direction of this weight? For your own weight, do you have any direction? It
So,
can be,
but when we
look, it is only a mathematical side. For velocity, we are going from point A to point B with a certain velocity. Acceleration, we are going from point A to point B with increasing speed. That is a definite destination you are going. Okay? Distance
sir, but the
from
sir,
here
but the
to here.
time of solving questions
That is the
in our
conception.
solid mechanics.
Temperature, if you see what is the amount of heat is moving from here to here, otherwise you cannot have the range in temperature. Okay, I agree. But as a value, that does not require any direction. If you
No,
go to
sir,
the
I'm
depth,
talking about weight.
look, if you go through the depth of changing temperature, it is also changing. If you go for the application of how it changes, heat is being applied to it and up to a certain direction. But heat is not never.
No, sir, not the temperature. Not the temperature. I'm not talking about the temperature. I was
I
talking
know.
about
You
the
told
weight.
the vector. You told about the weight.
Yes,
These are only the values.
because at the time we solved problems in solid mechanics where we used free body diagram. We used to direct the weight towards downwards.
We
It's a direction now.
no. In solid mechanics, we will use certain forces, body forces. We'll soon come to it. Certain body forces, but they are used as a forces. Say magnetic forces acting over a body. Earth's magnetic forces. Actually, that is create your weight. That is acceleration. That is scalar vectors. But we are defining it a different way as per our own benefit. Okay?
Sir,
Let us
sir,
stop
one
this
more thing.
discussion and move into more details.
Sir,
You can
so one
ask,
more thing. One more.
we can argue about the scalar vector for a day. It will not lead to
So
any.
can I ask you one more thing?
Bolo.
Can I ask you one more thing? If a dot product one scalar quantity and a vector quantity, what result we would be getting?
Look, what you have to do here only, what is told to you.
It's simple.
Because, look, let me finish. There are stresses. Here they are using a scalars. But
No,
force
if we dot product one scalar
Why?
quantity and a vector quantity,
Huh?
then if we dot product one scalar quantity and a vector quantity, what result we would be getting?
Achha. Let us see why we can do it. ठीक है? Feet degree scales, these are scalars, but nothing more than real one. But we can tell the letters are normal or ordinary letters. Okay, let us go for the subject at the beginning. Question is, so let us start with the stresses. We know the stress is when a concept of stress is when a bar is under of uniform cross section, maybe not non-uniform cross section also. Mostly we can assume circular rod for our own benefit. Rod can be square, rod can be elliptical, rod can be rectangular, etc. But generally we think of circular rod. Now if rod is subjected to tensile force acting along the axis, means just 1 second. Now, the it is subject to tensile force along the axis of a bar. Okay? So, what is stress? We know it is the resisting force created in the bar to resist the external force, and it is the force divided by the cross-sectional area of the bar itself. Resisting force and resisting stress is resisting force is the total force, and resisting stress is force divided by the cross-sectional area of the concerned representative bar. We are assuming it is a round rod itself. Now, it may so happen a structural density may not be uniform. We are initially assuming this is a uniform bar, but in structural members, it is not processed uniformly. Bodies may not be uniform in one hand, or stress may not be uniform everywhere across the cross section. The load acting over it may be only not just one, not a single simple tensile force, but multiple stresses, like we have discussed in our strength of materials. But we are assuming for a particular cross section, the stress is uniform throughout the cross section. So, what we may say, when we have found for a single cross section even, stress is not same everywhere. And if you make a assumption that is the same everywhere, your calculation may be wrong, because you are assuming an average stress. You are not going through the maximum stress, you are not going through the minimum stress. Okay, so when you are designing, your calculations may be wrong, because average stress or average force is much less than, may be much less than the maximum force or maximum stress. And the maximum stress or maximum force will create a predominant part in this, supposed to be make a predominant part in your design, which we are supposed to go through. So we have to find out what is the maximum stress and what is the maximum stress on a point over that whole cross section. A cross section can be a infinite made of an infinite number of points, and it has a infinite number of stresses. May be equal, may not be equal, maybe minimum, maybe maximum, maybe average. So we have to know what is the point over which the maximum load is creating. For a crankshaft, automobile crankshaft, or a car, or your mobile, your two-wheeler crankshaft, a piston inside a cylinder, and aircraft wing, all are subjected to loading. These are much more complex and dynamic in nature. Complex means they are not, stresses are not equal in all the points. Dynamics means stresses are variable in course of time. Both we are not taking into account so far. We think it is average, but now we have to take into consideration of the change in the forces across the cross section, and how will you meet? We have to know that. So here we have to introduce the concept of the stress, state of stress at a point, and its analysis. So we should not deal with the force that varies with time itself. Just 1 second. It will be assumed now here the matter of the body is not discrete, it is homogeneous. It is being considered is continually distributed over the volume, so that we can consider a small amount of element or infinitesimal volume, or a volume equal to dx, or a matter equal to of a size equal to dx, which is a differential element. If the matter surroundings a point and shrinks its volume, we should not come across a void, it will be perfectly solid. And all the materials are composed of many discrete particles, which are often microscopic and which are arbitrarily, maybe your random or personal choice, selected volume element is shrunk by the action of the external forces in the limit, and one may end up in a void. There are certain places there is no material at all. But we'll always assume our concerned member is perfectly homogeneous, it's continuously distributed, there is no voids anywhere. This is the assumption first we are making. And so here also we are not hesitating to make certain assumptions. Now, such a body is called a continuous medium, and mechanics of a body is continuum or quantum mechanics. Let us consider such a body. Say a body here, like this irregular shape. Consider this is the bodies in a region of shape. Consider to a rectangular coordinate system. Refer to a rectangular coordinate system like say OX, OY, OZ like this, which is mutually perpendicular to each other and representing three mutually perpendicular directions. The body will subject two types of forces here. One is body forces and another is surface forces. Subject forces and body forces, what are the body forces here? A certain body, whatever may be small, it has a certain inherent forces. It acts on each and every volume elements of the body. What is the example of such body elements here? Let us go through that. Say gravitational forces, the forces which is creating your own weight, the inertia forces, and the magnetic forces. Inertia forces may be there, and magnetic forces may be there if it is a magnetic material. Mostly you are using different type of steel. Not different exactly, I'm wrong. We are using only mild steels. That's very much magnetic. It has a certain weight, so it has a pull from the gravity. It has a gravitational forces. It may have some inertial forces. It required certain amount of forces to move it when it is stable, and required certain amount of additional forces to stop it when it is moving. But this type of gravitational inertia and magnetic forces, we are talking about the body forces, which in strength of material we have not talked. We have considered only the external loads, and sometimes is in very rare cases we have considered the weight of the body, but generally no. The surface forces acting on the area limits of the body when the area considered lies on the actual boundary of the body, this surface force distribution is called surface tension attraction. So when you are considering an area, taking an area which is exactly on the surfaces, not inside the body, and say on the boundary, on the surface itself, the surface forces distribution generally is called as surface traction. In the figure, the forces F1, F2, Fn are concentrated forces, while P is a distributed forces. The surface reactions are also the surface forces. Surface reactions, they are also surface reaction forces. This is exclusively assumed that under the action of both body and surface forces, the body is in equilibrium. Body forms an equilibrium. In the last, what you have seen in the last pages, What is seen here? Some R1, R2, R3, etc. Some forces P, some forces F, F1, F2, F3. These are the certain external forces or surface forces. These forces are acting on the surface here, here, here. And all these surface forces have the reactions because all your beams are supposed to be on certain faces itself. And it is supposed to be on the, just one second. All this supposed to be on the reaction itself. All surface forces supposed to be carried by a certain supports which will create reactions. We have other forces like P. What is that? All this P is a distributed forces. Surface forces are concentrated, single, individual forces which we have gone through the strength of material, distributed forces, maybe there, maybe individual forces, but their effect is slightly different. Here P is a distributed forces. And all these forces P, F are being supported by the reactions R1, R2, R3, etc. It is explicitly assumed that under the action of both forces and surface forces are the body forces and body is in equilibrium. Here is also we are saying that the body is supposed to be in equilibrium. Let P is a point inside a body, which are shown in various pages with coordinates x, y, z. And we cut this body P, this is here, here, in two pieces. May not be exactly equal arbitrarily. One part is called C and one part is called D. And we have divided it through the point P here, here by a plane 1, 1. It is not shown here, but shown in the earlier pages. If we consider the ABD, free body diagram, what will be at? If we consider the forces of C and D, then each point is in equilibrium. What is the free body? We have divided a surface, divided a body into equal parts, and we are showing the effect of the other part over it by the action of the forces, and we are cancelling these imaginary forces exactly equal amount of showing it in the exactly equal amount to the opposite forces but in different reactions in opposite direction, acting in opposite direction. Now, each part is in equilibrium under the action of the external forces applied and internally distributed forces across the interfaces. Now in part D, say, let us assume a small area surrounding the point P in such place in part C here corresponding to the area P dash in delta A here. These two areas are distinguished by the outer drawn at N, and here is N dash and N dash, not exactly N dash, but N to the power suffix 1. This is N here, here, but not dash. Dash is here. 1 is N, En here. It is a normal to this force itself. The action of the part C on AA on this force here can be represented by the force vectors delta A to the power to the power 1, which is a vector, so here we put it at 1. And the action of the part D at A dash at P dash is the forces delta T dash itself. Now, assume that as a delta is tends to 0, means it's infinitesimally small. We are closest to 0 but not 0. Ratio delta A t dash by delta A tends to be a definite limit. And further, the amount of forces acting on the area delta A about any point within the area vanishes in the limit of the limiting vector, which is delta t dash divided by A, delta dt by A divided by T, which is the stress. Similarly, at the point P dash, here, the action of the part D over C on A dash tends to 0, represented by vector limit A dash tends to 0, delta to the suffix 1 dash divided by delta A, delta T dash A by dA 1 by T. Thus, the vectors are called the stress vectors. Both these vectors here, T dash and T dash bar dash, T1 dash, T1 are the stresses defined as the stress vector. In the same way as we earlier decided what is stress and what is stress. It is a stress vector and it is denoted by the term 1 over the top. Here, the P and P dash on the planes, which are outer drawn and with normal N dash and N1 dash. So the planes, we are also defined a normal drawn over the plane itself. The stress vector T here correspond to the action of C and D at P is equal to a magnitude and opposite direction to the stress vector T dash, represent the action of D on C. And so we are here representing stress vectors, the action of C on D and action of D and C. And same T and T dash, we are representing as stress vectors. And the action of D and C, this assumption is similar to Newton's third law. Applying the force, so you have T dash is equal to T dash.